Pleased to introduce Deb Ray, Chief Data Officer for VideoAmp, which is a startup based in Santa Monica. He's going to tell you about enabling cross-screen advertising with machine learning and Spark. Deb.
Thank you very much for the intro, and thank you guys for coming in right after lunch. So I'll start off slow and then pick up the pace. So VideoAmp is a startup out of Santa Monica. We started 2 years ago, and in the last 2 years, we've grown our team to about 48, and we raised $18 million in funding. And now we work with some of the biggest ad agencies and brands. And our core offering is a cross-screen advertising platform. And in order to come up with our platform and serve our platform, we have to use a lot of machine learning. And to deal with the scale, we have to rely on Apache Spark. So in this talk, I'll go into that in more detail. So VideoApp came about because there's been a fundamental change in consumer behavior. And the way media is consumed is, it's screen agnostic. So the same program, Game of Thrones, people watch it on tablet or TV or desktop, on their Xbox, Roku. For the new generation, there's really no distinction between a TV and another screen. The TV is just a bigger screen. So the same consumer watching the same content in multiple different screens and formats. But the way advertising is sold right now, it's sold in silos. So if you want to reach the same consumer watching the same show on their desktop, you have to go to one exchange. If you want to reach the same user, same content on mobile, you have to buy from another exchange, like InMobi. TV, completely different story. There's another whole way of buying advertising on TV. OTT, you have to go talk to Hulu about buying ads there. So reaching the same consumer on the same show becomes problematic because now you're using all these different mediums and different channels to get to the same person. So what's that done is created a gap in the market. So ultimately, the advertiser, say Corona, reaching one user on a site like Men's Health or on an app like Zynga, has to go through so many different intermediaries. So they have to go through exchanges, ad exchanges like LiveRail, providing Facebook inventory, or OpenX. And there's DSPs, demand-side platforms, that then enable advertisers to buy on these exchanges through real-time bidding. And then there are data management platforms like Nielsen, Kantar, Comscore that provide data about the user. So there are multiple different pieces just to get advertisers to reach their consumers. And the goal of VideoAmp is to make this process much more efficient by using data. So the goal of our company is to enable advertisers and content owners to transact seamlessly across all media types. And we do that by bridging the data gaps across all these different platforms. So the advantages of doing that is you can do frequency capping. So the same consumer need not see the same ad show up every time they open a different browser or they go from one medium to another. And also, the other thing that it does is it allows us to go, or advertisers to tell a story. Rather than show a creative one piece at a time, we can tell a story from a TV to mobile device to a desktop as the consumer goes about in their journey. And it also enables other things like competitive conquesting. By that I mean, if you find that a competitor brand, or now with the political season, if you see a competitor's ad on their TV, we might be able to target them with another ad on their mobile device. So that's called competitive conquesting. And we can do all that if we have access to a consumer graph. What I mean by that is the same user, so a consumer graph is a consumer with all their devices that they use together. So the graph connects all the devices that are used by the same consumer. So one way of constructing this is the same consumer goes to their phone, so that we get their IDFA. They are on their Safari browser on their phone, so that allows us to connect the two together with the device IDs. If we see the location indicators like IP addresses or geolocation, we can see the same consumer is on their phone, but on their home, on their Firebox, so that's yet another ID. On the same computer, they could be on their Chrome device that allows us to reach the consumers across the different browsers that they're using. And through login data, we can reach across to another location, like their work computer, for example. So by tying the data together from all these different devices, each used for different purposes, we can see a much more comprehensive picture of the consumer. So that's all good, but we're dealing with enormous problems of scale. So in order to build this graph, we typically deal with 1.5 to 2 billion unique IDs, cookie IDs or device IDs. That boils down to about 150 million nodes, right? That all go into the graph. That's the size of the graph. And we're collecting behavioral data from each of these IDs, which sites they go to based on the ad opportunities they see. So this results in several terabytes of data every day. So that's the part of scale, the volume of the data that we have to deal with, and the scale of data, the magnitude of the data that we have to deal with. The other complexity in real-time advertising, in real-time bidding, is latency. So, for those of you who are not from the ad tech world, what happens when a user goes to a site and they see an ad? When they go to the site sends a call out to an exchange, right? So if it's one of LiveRail's network, they'll send a call out to LiveRail exchange. The exchange then sends out a bid request. Everyone who has a seat on the exchange. So VideoAmp has a seat on most of the video exchanges out there. When the bid request comes out, the real-time bidder gets passed a set of parameters like the user ID, IP, and so on. From there, we have to run a decision engine that takes all these parameters and what we know about the user that we query from a database and come up with a bid price. Okay? And we have roughly about 20 milliseconds to do this price calculation. From the bid price, it goes back to the exchange where it enters the second price auction. And if the winner of the second price auction gets to serve the ad. So all that has to happen in roughly the time it takes a website to load. That's about 100 milliseconds. So in addition to dealing with complexities of size, we have to also deal with latency. It has to be quick as well. So that's why it is very important that we pick the right tool for the job. So from pretty much day one, we built our entire platform on Apache Spark. So about 5-6 years ago, it was Spark was a project out of Berkeley's AMP Lab. And the key innovation in Apache Spark is this concept of resilient distributed data sets, which is a logical collection of data partitioned across machines. So you can have a cluster of commodity machines, and we're able to utilize and do computations in memory on overall those machines. And the other thing that has happened is memory has become more and more commoditized. So memory is cheaper, so we can run a large cluster with with a lot of memory. Spark also has the key APIs in Spark are Scala, Python, and Java. In our stack, the Spark runs on top of HDFS for just the data storage, file storage format in Parquet. And what we have seen and what's been benchmarked several times is for iterative applications, especially, which is the case for a lot of machine learning applications. Spark can be up to 100 times faster than doing the same sort of jobs on MapReduce. So these are huge advantages that we need in order to be able to do the things we need to do. So in particular, for the consumer graph, we relied on a recent innovation from the Spark project called graph frames. So graph frames is a graph processing framework. It's similar to GraphX, for those of you who know. The APIs are in Scala, Python, and Java. What it enables you to do is run queries on graphs similar to Spark SQL. So, the code looks as simple as that. If G is the graph that you have, it's a graph object, then you can run a query where you look at all the vertices and filter by all the consumers that are greater than age of 25. Or I can run a query that tells me all the nodes that have in degrees or connections greater than 2. So these are very simple things to run using graph frames. And graph frames also supports other algorithms like breadth first search or connected components or label propagation algorithms. So internally, we had a project called Flint. We created this project, or the need for this project was to satisfy a lot of on-demand jobs, mainly batch processing jobs or ad hoc querying jobs. So our project, internally named Flint, allows us to create push-button Spark clusters for machine learning and data science in the cloud. And we are planning to open source it. So for some of you who might be interested in testing this out, come and talk to me or one of the folks at VideoAmp afterwards to get you on to test this out. Flint is designed for rapid deployment while providing native access to the data in HDFS or Hive cluster. So there are 3 components to this. One is Flint itself, which is a Spark cluster launcher on AWS for now. Also contains self-contained Spark Docker images. So it can run on, it's containerized, can run on any type of hardware. And we also include a Jupyter Docker image. So that comes preloaded with Python, R, and Scala kernels. So it's very easy to spin up a whole new cluster and do your data analysis on top of it and spin it down. It's easy to expand or contract the cluster by adding new nodes or removing certain nodes. So let me do a demo of Flint. So this is the Jupyter notebook. For those of you who are not familiar with Jupyter, this is it allows you to run code within. It's an IDE, but you can share it. It's on the cloud. It's an open source project. So here I can add different classes. So before I start going to the code, the way we package this, it comes with R, Scala, Python, right? So to run your different data science jobs. We can add new class paths very easily. And then starting up Flint is as easy as pulling in the configuration file. And we can set up our own configuration for the cluster that we want to launch. So, here we'll name it my Spark app, for example, and give it an endpoint. In the configuration file, you can put in your own AWS credentials. And we can specify the number of cores that we want. We can put it 128 or 1,000, whatever your budget allows. And then choose the executor memory sizes. So what it does, right after it launches the whole cluster in AWS. Right, so now you have that available, you're ready to do your data science or machine learning on top of it. So I can import whichever libraries that I want. So I can import Spark SQL, I can import graph frames, any other type of libraries. Once I've imported these libraries, I can go around and then whatever code I need and call my HDFS, call data from my HDFS cluster. So if you are interested, taking it for a spin, come and talk to us. Okay, so going back to the problem we're trying to solve. So we collect data from multiple different devices. And we collect data from TVs. So this is data from smart TVs. A lot of the TVs that connect to the internet Through partnership with OEMs, we can collect the viewership data from some of these TVs. So in data in 15-minute increments, we can see viewership behavior from the TV. The sample size is about 10 million smart TVs right now, or set-top boxes. We collect data from mobile devices, so about 300 or so different unique device IDs. That gets around 50,000 queries per second through the bidder. And from these devices, we get sites, video content, segments, and so on. From desktop, it's a bit larger, about 1 billion cookie IDs, do about 100,000 queries per second, and get sites, video content, segments, like their user segments, behavioral types, and so on. So that's a lot of data, and it's hard to work with that data alone. So we need to create a more compact representation of that data. So we have a sparse representation where we take a certain class of data and we enumerate all different possibilities. We created this dictionary of all different values. So an example is, if you take a demographic segments, look at income and divide that. You can get discrete values, and an indicator variable indicates what that user, which group that user falls into. Or for content like TV programs to watch, we can enumerate and create a dictionary of all the entire universe of different TV programs. It could be 50,000, 100,000 with different TV shows, right? And if I want the data for a particular user, I just have a vector, a sparse vector with ones in the programs that they've seen. This gives me a very compact representation. And this compact representation allows us to do a lot of computations. So with the compact representation, with the sparse representation, we can construct a graph. This is kind of a cartoon schematic for it. Initially, we don't, the picture shows that it's all grouped together, but initially we don't know that they're grouped. So the top right, there are 3 different devices there. Device 1 could be a mobile device. We can collect behavior data there. Device 2 could be their computer. We can collect segment data. Device 3 could be a TV. And we can first group them together. The first pass of grouping them together could be things like location data or IP addresses. But we can go a level further. With IP addresses or location data, you can narrow down pretty solidly to an individual household. But in order to get further within the household and find individual users, we can go a step further by looking at the behavioral data. So an example of this, if you look at the top right, the schematic shows that we have pooled together 4 different devices. But if we look at behavioral data, then it's easy to see that within a household, it might be possible to separate male and female viewers and also age, right? Just you get 4 different quadrants right there. So behavioral data allows us to go much further and create and identify actual users, like the unique users and their associated devices. So there are multiple ways of constructing a graph like this. One is through connected components. So you have a bunch of nodes. That diagram over there shows that there are 3 connected components there. So a connected component is a subgraph where you can draw a path from any one vertex to another. And in order to find the connected components within a graph, the algorithm is to start with any arbitrary node and do breadth first search and find all the connected components there. And keep repeating this process for every unexplored node. One of the drawbacks of connected components is it ends up creating much bigger graphs or much bigger nodes than we want. So we need to do a further process of refinement. Right? So an example could be if you visit your friend's house and connect to their Wi-Fi, now you're in a connected components analysis. your device can now be associated with theirs. So we need to go and do another step of refining this process. So something that refines is clustering. Just to give a schematic again, the data looks like, so if you start with location data, you can see a scatter plot of different locations for these different devices. You can run a k-means or any other clustering algorithm from the location data alone and group them into different clusters. On our side, we get a lot more data than just location. We get location, IP addresses, types, gender, and also behaviors. Very important behaviors like websites, TV programs viewed, certain third parties provide purchase data. So we end up with data in a very high dimensional space. Sparse data in a very high dimensional space on which we do clustering. So once we have the graph, and now you've seen the original graph, now when we do inference, we collapse that graph into individual nodes. Each of the nodes now represent customers or consumers, and we pool the data from all their devices into one. And now we have a representative data set for each consumer in each node of the graph. This allows us to run a lot of very interesting graph inference algorithms. So one is simple lookalike model. I have a user A, and I want to find all the users like them, so I can target them. We can also fill in missing attributes through graph inference. So if we don't have a certain data set for one person, like their income level, we can infer that value because of their similarity to other users in the graph, using behavior and other attributes. And also a real-life example that we dealt with recently is there was a pilot coming out for a show. It's a zombie political show called Brain Dead. Please tune in. And the show supposedly is like it's a combination of Walking Dead and House of Cards. So, well, how do we find users who might be interested and might want to tune in? We looked at all the users that liked shows like Walking Dead and people who like shows like House of Cards. Then we got a set, and then we target them. Then we can observe their behavior using different APIs. Did they tune into the show? Did they engage with the ad and so on? And further refine that. So now we have a set of users who we predict would like Brain Dead, the show. So, so far I've described methods that are more unsupervised because we use connected components and clustering. But there are many parameters within machine learning models that we use that need to be trained. So we need some way to validate that. We need training sets. So for example, when we construct a graph, we need to find a threshold for this edge distances for machine learning purposes. For that, we use login data as validation. So, best example of that is Google has tons of login data, which they don't care, but internally, they can use their login data to see the different devices you've used to connect to Gmail, right? So they don't even need to use unsupervised approaches because the login data is so large. But we work with multiple publishers and use the login data as a validation data set. And the key metrics we're trying to learn in order to fit our parameters are precision and recall. So when we construct our graph, precision is the devices that we have directly ascribed to a user. Okay? So that means high precision means that when I say a device is tied to a user, we're right about it most of the time. And the other variable, if you drive up precision, it can come at the cost of recall. So for recall, it means how many devices are actually belong to the users that are correctly identified. So sometimes it's possible to drive up precision at the cost of recall. For our particular problem, recall is really important. precision is, but recall is extra important because if we want to target a set of users across their different devices, we need a high recall rate because we need to know and assign all the devices to a particular user. So our algorithms try to find the right balance of precision and recall with a particular emphasis on recall. So I'll give a more concrete example of this, of one of the problems that's easy to visualize. So let's look at TV viewership classification. So we get data from TVs through audio content recognition. And each TV ID generates a vector of program viewers. So we know, like, for a particular program, let's say Walking Dead, out of our pool of 10 million users, how many saw that? Right? So we get a sparse vector, again, of users who watched that show. So think of it as, for those of you who know, word to vec, where each word now is a particular TV show, and then the vector represents which user saw it. And from that, we can now use our clustering algorithms to learn an embedding. So that's all good. We have learned this embedding in this 10 million dimensional space. How can we actually visualize this? One way of doing that is using T-distributed stochastic neighbor embedding, which maps a high-dimensional space to a low-dimensional space, like 2D, that we can visualize. The advantage of TSNE is it preserves relative distances compared to an approach like principal components analysis. So this is just a scattered plot of all these different TV shows and their relative distances from each other. If we zoom in further, it's an example. This is a cluster we found of TV shows that all seem to be about space exploration. And the relative distances show you the similarity between these different shows. So, we know that ISS Expedition is kind of similar to NASA X, but not as similar to Mission. So I'll end here and take any questions.
Questions? For writing the data transformations, are you using Spark SQL or what are you using?
Good question. So the data, for pulling in the data, we pull in using Spark SQL, which is the whole, and then to do the transformation, we use Scala. So we turn that into dictionaries and create a Spark vector representation. Anybody else? Yeah. So the longer term, the data is stored with RK format.